to share future announcements with your cohorts. Also, we are recording most of the seminars and they will be posted on the department's YouTube website. So without further ado, let me introduce today's speaker. Dr. Jewell Bergerson is an associate professor in the Department of Chemical and Petroleum Engineering at the University of Calgary, which is in Calgary, Alberta. She holds a Tier 2, I think this is correct, Tier 2 Canada Research Chair in Energy Technology Assessment. And she's a member of the Royal Society of Canada College of New Scholars, Artists, and Scientists. I always wish I could be a member of a Royal Society. But she received a joint PhD in Civil and Environmental Engineering and Engineering and Public Policy from Carnegie Mellon and has been on the faculty at Calgary since 2008. She directs an interdisciplinary and collaborative research team and is a global leader in the development of new methods for energy technology assessment, contributing to the development and broader use of system tools in the energy sector. She has a long list of publications in some great journals like Science and Nature and Nature Climate Change. And she is working on getting her, her work includes adoption of her research results directly into policies such as California's low carbon fuel standard and policy relevant tools related to the United States. Without further ado, I want to welcome Jewell for coming to talk to us, and I'll give her the floor. Welcome.
Great, thank you very much. And I'll just share my screen here. So I'm excited to be here today to chat with you. It looks like we've got a good turnout of people here. Always would have been better to do this in person, but I'm still excited that maybe we can have some dialogue on this topic throughout the session today. So as was said, I am from Canada and am at the University of Calgary. And so I thought it might be helpful to give you a little bit of orientation to start out. We're making some pretty big decisions these days about our energy future. And I'm going to talk specifically about the way that technology assessment tools such as life cycle assessment, techno-economic analysis can help at the early stage to inform some decisions that we're facing. But I thought I might give you a bit of a contrast in terms of our geographic region, our challenges, and how we're thinking about the energy transition that is before us. And so just a little bit of background about Alberta. So this is the map of the province. It's on the western side of Canada. The west side of the province is the Rocky Mountains in Canada. So we're just above Montana landscape, and looks very much like the Yellowstone show if you're watching that. Foothills and mountainous region sort of landscape. We have a population of about 4.4 million people, but our land area is about the same as Texas. So a lot fewer people, much more sparsely populated land area. And, we make a lot of parallels between Alberta and Texas in terms of our oil and gas sector. But I think it's important to note that it's a slightly different dynamic. There's some things that are similar and we can learn from each other, and other things that are a little bit different. So this is our GDP in 2015 for the province. And you can see that our largest sector contributing to GDP is our oil and gas and mining at 18.3%. And because it is such a large sector, it also contributes then individual components of all the other sectors. So there's spin-off effects of our oil and gas industry that really do permeate the economy. And so when we talk about energy transitions, either away or a modified version or different types of resources, we really need to keep this in mind in Alberta in a way that most other jurisdictions don't have it as prominent. The other piece to this is that our energy demand profile looks quite different than most sectors. So Texas, while we see the parallel with oil and gas, it is not such a big driver of the GDP. It looks like it's on the order of 7% as opposed to our 18%. And then when we also look at this breakdown of where is the energy going that we're producing in the province, we're quite unique in terms of being dominated by industry. So when I looked for Texas, industry was about 50%, and that's still quite large compared to most jurisdictions, but we're at 75% of our energy is actually used to support industry. And that includes the export of the oil and gas that we produce, right? So the export component of our economy is something that also affects our decisions about our energy transition over time. So another component to think about in terms of the dynamics and the uniqueness. The other thing is the reason why we've got to this place and have created an economy that is very dependent on the royalties and the economic value that comes from our oil and gas industry is that we sort of punch above our weight. For 4.4 million people, we have assets like our oil reserves that are some of the top in the world. And that sort of distorts discussions or changes discussions when we can attract international investment and sort of punch above our weight in terms of the role that we can play in the global oil sector because of the assets that we have. And of course, the majority of these are heavy oil and ultra heavy oil in the oil sands deposits. So have additional challenges in terms of the economics as well as the energy intensity and greenhouse gas emissions associated with producing them. But it's not just oil, it's also our gas deposits as well. And again, we're punching above our weight for 4.4 million people in terms of the global production. This is not just the reserves, this is actual production of natural gas. And so that also plays into the discussion about the role that it has in our economy and how do we think about our energy future and our economic system moving forward. And it's not just oil and gas. It's also, we have some of the best coal deposits in Canada and all different qualities of coal. We've primarily used coal to generate electricity in the province, and that's only now shifting as gas becomes cheaper, that we're shifting to more gas. But historically, we were up to 85% of our electricity came from coal-fired power. We're even having conversations in the southern part of the province about opening up new mines to extract metallurgical coal. So we've got a whole range of hydrocarbons available to us. And what that means then is that we've got this wealth of energy resources throughout our province. It gets quite messy when you try to put all of those on a map of the province. And what's not really reflected here is that we have some of the best wind and solar resources in the country as well. So that's an opportunity. We still have hydropower, large scale hydropower that has been undeveloped. That is a potential resource moving forward. We don't have any nuclear in the province, but we are next door to Saskatchewan, who is the #2 producer of uranium in the world. And so we've got access to a broad range of energy types, and we've developed some of these. We have the potential to develop others. And so we really are at this crossroads of where do we go with our energy system, and then it being so entwined with our economic system. We need to think about both in tandem as we think about our energy transition. Just a couple other things. International low oil prices really do affect us even more so than most oil producing nations, given that we have some higher cost supply options of our oil. And so that's affected us quite a bit over the last decade. The US is really our only energy trading partner to speak of. And so we're historically have been exporting our oil and gas directly to the US and to the US only. And so energy independence, the shale gas revolution, all of these things have benefited the US and have had an impact on Canada directly, given that you are really our only customer associated with these products. And so that affects things. With the new administration, you might have been talking and looking at all different aspects of Biden being inaugurated. In Canada, the conversation was really dominated by the Keystone XL pipeline, and that it was shut down within the first week of his administration. But also the aggressiveness with which Biden is going after climate, and that shift in perspective on climate initiatives in the US will have pretty significant effects in Canada as well. At the same time, Alberta is experiencing extreme events, and that is changing public perception about that climate change is real and that it is starting to affect us already. So we've had some pretty significant forest fires, both in Alberta and BC, that have affected our air quality. We've had floods and those kinds of things. And then lastly, just the climate related policy and strategy. And we have a pretty big discrepancy between the perspectives of the provincial government versus the federal government in Canada right now. So the federal government has reaffirmed a claim of being climate neutral by 2050. They've announced a hydrogen strategy that includes both blue and green hydrogen. So blue being natural gas with carbon capture and storage, green being electrolysis with renewable electricity. And I would say I characterize the balance between the environment and economy from the federal perspective as really focusing on a low carbon economy moving forward. In contrast, the Alberta government, I would say that the economy environment balance is a little bit more towards reducing the impacts from fossil fuels and having them remain relevant moving forward. And so it's two different perspectives on the challenge. In Alberta, it's energy companies that are actually pledging to be carbon neutral by 2050. And a lot of that is discussions about technologies like carbon capture and storage, as well as carbon capture and utilization. And they've announced a natural gas strategy that includes export of liquefied natural gas, as well as the role that hydrogen can play both within the province, as well as a new potential export product. And so that's a lot of context. And then what we see, though, is that we have projections into the future. And so this is total primary energy in Alberta. The dotted line in the middle is where we're at 2018. And this is in petajoules of energy. And so you can see that this is one view of our energy transition, and it looks very similar to where we are today, so that we can maintain a very small fraction of renewables within our energy system, which is the top bar, and that everything else remains relatively similar, except that we still see our non-upgraded oil sands bitumen continuing to grow over time. Right? And this is not congruous with the federal plan to be carbon neutral by 2050. And so this is part of the conversation we need to have is how do we move forward with the economic value that we're getting from these resources and the potential that we see to grow those resources while still meeting climate targets, and both because of federal pressure, but also international pressure that seems to be growing in terms of pushing to attain these climate targets. And so that's just to give you some sense of where we're at from a jurisdiction. You might have been a little bit distracted by some of the things going on in the US these days. And so maybe haven't got your finger on the pulse of what's happening just to the north of you. And so I thought I might give you that as a starting point for discussion. And to start it by saying that we have challenges moving forward internationally, but that are regionally specific as well. And we need to think about that. But at the end of the day, we need to confront the issue of these climate targets and how do we best attain those within each of these jurisdictions and think about that transition. And so if we are seeing trajectories like this forecast, how do we do this differently with fossil fuels in order to get that balance between economy and environment? And so that is the role that I see as contributing to this discussion, is the use of technology assessment tools to inform the energy future, and particularly doing this at an earlier stage of development than we traditionally do. And so my premise here is that system tools are underutilized, but actually can be used to not only facilitate the dialogue, but also help to drive the innovation process itself. And so they can be embedded within the ideation process as you're coming up with new concepts and technologies that could play a role in this energy future, but also to improve the designs, process designs, prioritizing research, development, and deployment, ensuring that the goals of innovation are actually achieved, and then avoiding potential unintended negative consequences associated with that. So that's quite a bit for one set of tools, but I do think that right now what we're using these tools for is typically at commercial scale once we've already deployed technologies. And the idea here is that if we can get these tools in earlier to the development process, you can potentially have a bigger impact on the types of designs that move forward that potentially could deliver what we're looking for with the minimum of negative unintended consequences. And so if you're not sure what I'm talking about when I say systems tools, it gets used differently in different contexts. But here I'm talking about decision-making tools like life cycle assessment. And so life cycle assessment is a tool that allows you to identify the environmental burdens and evaluate the environmental consequences of a product, process, or service over its life cycle. And so you can see in this figure here that we have material extraction, manufacturing and production, transportation, utilization, and then disposal of unwanted residuals. And so this is thinking about that entire supply chain and its interconnectedness to make better decisions from a more holistic perspective. So it helps us to structure the way that we think about complex environmental issues. And most of the issues we're dealing with when it comes to environment these days are more complex. So we're looking at trade-offs between cost and greenhouse gas emissions and water use, those kinds of things. And so life cycle assessment can be really helpful to do that. From an engineering perspective, life cycle assessment is basically just one large mass and energy balance. So you're looking at all the inputs and all the outputs associated with each process unit, and then scaling that and connecting it to the entire supply chain of that process unit or technology. And it started in the 1960s to inform policy within companies and to set government direction related to energy. And it's been changing over the last decade or so as we institute things like the low carbon fuel standard in California or the clean fuel standard that we've announced at the federal level in Canada, because there's actually connecting the supply chain to look at the emissions and actually regulating based on that life cycle intensity calculation. In addition, investors are now starting to ask for more information earlier in the process. They want to make sure that what they're investing in is not going to create a new environmental problem downstream, or that there's no unintended consequences that they might need to be aware of that increase the risk associated with that pathway. In addition, they want to understand any of the carbon risks or liability associated with a project. So even existing oil and gas operations are being asked to supply this information so that investors can make decisions about whether or not that makes sense within their portfolio. And so this is the traditional, and as I said, in traditional life cycle assessment, we wait for the technology to get to commercial scale. And then we apply these tools when we have rich data sets and multiple years of operations and things like that. Here, what we're trying to do and what we're getting asked to do more and more is to assess technologies earlier in the development stage to have that larger impact. And what we found is that there's good guidance about doing life cycle assessment at commercial scale. When you try to do it with less data, more uncertainty, we need some additional discussion as a research community. And so we started out this research network and actually ended up having a special issue in the Journal of Industrial Ecology that was related to the life cycle assessment of emerging technologies. So not just energy technologies, emerging technologies in general. And so we got a group of scholars together, and we wrote one of the papers in this special issue looking at evaluation techniques at different scales of market and technical maturity. And through conferences and through this special issue, we've created a research network that's actually adapting and developing new tools to assess these technologies when we need to think about them from an emerging technology perspective. And so we're now working on collecting that group to put in an NSF RCN grant, so a research coordination network, in order to facilitate more of these dialogues associated with this. If I just jump into that figure, which is this sort of summarizing figure from our paper, this is two axes that we need to start thinking about and to structure the types of tools and analysis that we can do. And so the first one is technology maturity. So you have technology readiness levels to help characterize something from a concept level all the way through to commercial scale. And then we also were talking about the fact that market maturity is important as well. So you might have a revolutionary technology that's just going to replace and substitute in for another technology. And conversely, you might actually create a new market by introducing this product. And so one example there would be the bitumen beyond combustion effort that's in Alberta to try and make use of bitumen in different ways. And so making carbon fiber out of bitumen that might create new markets for carbon fiber as an example. And so for each of these different categories of technologies and markets, there's going to be a different set of research questions that you can ask and that maybe you should be asking given the level of data availability, the types of questions that are being faced at that stage of development. And so this was just a starting point, but just to say that there is a growing community of researchers that are actually evaluating and using and developing these types of assessment tools. This is a slightly different way to think about it. This is the technology development process that is made much simpler than it actually is in the real world. But you start with your concept or idea, you go through some modeling and lab experiments, some pilot testing, you get to a field trial, and then you have your technology commercialization. And if only it would work that simply. We have lots of iterations through this process, and oftentimes we sort of go off the rails on this because we find that during the modeling or during the pilot testing, something fails associated with that process. And we have, within your technology or your research team, you have some of the analysis that you would do to determine when you get a concept that's worthy of going to the lab scale experiments. And so you do some basic mass and energy balances. And as you move through the development cycle, you start reducing the uncertainty of the physical systems. You start answering some of those questions. You get better resolution on your uncertainties, and you start proving out that technology. The life cycle assessment and other technology assessment activities, including techno-economic assessment, tends to happen when you get to that later stage. And what we would put forward is that there's actually a lot of value in getting us involved earlier, so that you actually start thinking right from the concept idea, playing through the full supply chain to understand, are you going to hit a hot spot in terms of energy requirements, economics, resource availability, all of those kinds of things right at the very beginning. And that can help you to rank concepts in a more holistic way that might give you some promising options a little bit earlier in that process. And then we can start elaborating on the assessments as more data becomes available. But the idea with this is that it does help you to fail faster. So you can actually play through a range of different concepts and ideas, think through some of the system-wide impacts that might occur, and help you to prioritize which of the different concepts you want to move forward to experimental stages. And then as you go through, continue to winnow down the options to make that technology development process more efficient and effective. And so to start with, though, we need to actually use these types of tools to set baselines and actually start demonstrating in a public, transparent way that is credible to investors and other groups that these things are actually at a certain level of emissions, and then we can start showing that there are emission reductions associated with these. And so this is a study that we did, which is looking at using our open source refinery greenhouse gas emission estimating tool. And we looked at data of refineries, it was 473, I believe, refineries globally. And we looked at the energy requirements and the greenhouse gas emissions associated with each of these. So this is one figure from our recent paper that is looking at refining intensity from the destination country perspective. So in Canada, we export a lot of our heavy oil, primarily to the US. And so what we refine in-house is more medium conversion type refineries, and we have imports of light oil and things like that. And so we have a lower carbon intensity associated with the refining than the US or somewhere like China, where there's a lot more deep conversion refinery activities that increases the intensity of refining each barrel of crude that is processed. And so the colors here are going from the dark blue at the low end of the carbon intensity through to the dark red color. And so we can do that for each of the refineries around the world, and we can then connect it into the full life cycle. So my colleague Adam Brandt at Stanford University has a comparable tool and a comparable analysis that looks at the extraction activities, so the energy and the greenhouse gas emissions associated with extracting different crudes around the world. We can then pair that with our refining capacity and then look at the downstream implications of that. And so this is really needed. It's surprising that this isn't in the public domain already. To me, at least it was. But now that we can pull that data together and put it in the public domain, we can have better discourse about where do we go from here in terms of the refinery of the future. How do we look at adding new technologies and new, adapt to new product demands in ways that make the most sense for these complex chemical plants. We can integrate things like not just carbon capture and storage, but potentially carbon conversion technologies to produce a new slate of products, those kinds of things. And we can evaluate what the impact of those new technologies might have on this sector. And so this was in that paper as well, was just the first attempt at doing that. And so in this case, we have each of the colors represent different types of refinery configurations, from hydroskimming all the way through to deep conversion. Each of the vertical rectangles are an individual refinery operating around the world. And then we've ranked those from lowest carbon intensity to highest carbon intensity. On the negative side, the green and the purple bars are mitigation strategies. So these are different levels of investment in reducing greenhouse gas emissions to show what the impact of these technologies could have in terms of reducing that overall greenhouse gas impact. And so this is it was a pretty aggregate study. The next step would be to actually look at individual refineries and the region in which they're operating. How will they respond to shifts in demand for products, and how might they adopt technology to reduce emissions further? But this was the starting point, and this is the kind of thing that we need as the baseline by which we can then start evaluating these technologies. Most of the technologies we looked at were relatively close to commercial in this study. When we're looking at emerging technologies, we have to think about other ways to assess these technologies. And so this is another example of a study that we've done. This one was looking specifically at carbon capture technologies. And so if you're at a power plant and you're looking at implementing carbon capture, we have technologies, primarily amine-based post-combustion capture technologies, that can take CO2 out of the flue gas of a power plant, and natural gas or a coal power plant. And what we were looking at here was, would it make sense for Alberta, this is an Alberta specific case, to actually implement the carbon capture technology we have available today? Or would it be better to invest in emerging carbon capture technologies where you might get a breakthrough in the cost, which is currently making this technology prohibitive, as well as the energy penalty that you get associated with running this carbon capture unit? And so do you wait, or do you actually implement the existing technology today, knowing that it's not quite as good as what might come in the future, but that we don't know when that technology might come online? And so these were 4 different scenarios for our electricity system moving into the future. And it was looking at the cumulative over 50 years, what's the net effect of these different technologies and different scenarios for deploying those technologies. So the scenario 1 is our base case, which is still a coal dominated grid, and we keep operating it, and we keep providing electricity using the same balance of technologies that we're using today. And you get this high level of emissions that are on this side at the 50-year cumulative side. And this was Monte Carlo simulation to allow us to incorporate uncertainties into this and propagate those to reflect this probability distribution over time. And then we had a scenario where we actually converted all of our coal plants to natural gas combined cycle units, and actually just built new highly efficient natural gas plants today with no carbon capture installed. And that's the blue set of emissions. So you get a large improvement over coal, but you're still on the sort of mid to high level in terms of the overall emissions in that 50-year time horizon. Scenario 3 is actually looking at this new technology of carbon capture, and the green is a coal plant that gets retrofitted with existing carbon capture. So we know quite a bit about our existing system, so we get this narrow distribution of emissions that we would expect to see if we retrofit our coal plants today. And then we have much more uncertainty associated with a new capture technology that we could put on our natural gas plants when it becomes available. And it could be better than the coal with capture today, or it could be quite a bit worse than that. And it could be similar to just switching over to natural gas. And so this gives us some sense for the relative competitiveness of this new technology. But it doesn't quite tell us enough about what would get us to the bottom end of this range versus the top end of this range. And so the next step that we looked at, we did look at this for cost as well. And there were sort of opposite ends in terms of the cost. It would be most economic to keep doing what we're doing today. But we wanted to look in, how else could we look at the potential for this new technology? And so this is the same study, same 4 cases that we looked at. The black is the advanced capture, the new technology that we want to understand. How much potential does this have to have an impact in reducing emissions? And it would only be able to have that potential if it came in as the most economic of the cases that we were looking at. And so what we did here is we had 3 different parameters that were sort of external factors that were uncertain into the future. So the level of carbon price that was being instituted, where natural gas price would be into the future, and then the capital charge factor that they could get for the capital that they'd be investing. The next 3 are about the technology itself. So when will the technology become available and commercialized? What sort of breakthrough do you get in terms of the reduction in the capital cost? And then what are the energy reductions in terms of the energy efficiency of doing that? And so 2 different aspects of the uncertainty going into the future. And then we ran Monte Carlo simulations, holding 2 parameters constant at a time and letting the rest of the system propagate their uncertainty. And so what we see in this top corner here is the carbon price is varying from $0 to $200 per ton. The natural gas price is varying from $0 per gigajoule to $20 per gigajoule. And each pixel in here is the outcome of a Monte Carlo simulation where we determine which of the technologies would be the most, or which scenario would be the most economic scenario at that set of conditions. And what we find is that for this technology, this advanced capture technology, to be competitive, the carbon price would have to be above $100 per ton, and the natural gas price would have to be below $10 per gigajoule. And so this sort of information can be helpful to decision makers where they want to understand, given a set of future conditions, how competitive will this technology be? And if you don't think that the carbon price will be above $100 per ton, then the prospects for this technology might not look as good as other technologies that might come in below that, right? And so these are the kinds of insights that we can generate. Similarly, the technology would have to come online within the next 20 years if the breakthrough in the capital cost would be less than $700 per kilowatt, right? That gives you indications. And so the technology developers that we work with can use these kind of outcomes to inform the targets that they need to set. How quickly do they need to actually get their technology to a commercial stage? And how much should they emphasize that scaling and piloting to get there quickly versus really focusing on the breakthrough in terms of cost reduction and or energy and greenhouse gas emissions impacts. And so you can sort of work back those targets at an early stage of development, given this type of analysis of where that technology needs to be competitive in that future scenario. So the last piece that I wanted to give you as an example of the types of tools and ways that we're using them is a new project that I'm working on with some colleagues at U of C, but also at the University of Alberta and the University of Toronto. And this is looking at the roles and risks of carbon conversion technologies. So I was just looking at carbon capture. Now I'm talking about the actual, once you've captured that CO2, how can you convert it into a value-added product? And what are the implications associated with that from an economic and a greenhouse gas emission perspective? The motivation for this is that there's a growing need to better understand how these systems can play a role in our energy future, and in some cases mitigate any unintended consequences where you might actually require more greenhouse gas emissions to be emitted for every product that you're producing, and wanting to avoid those kinds of issues. You'll see here there's a group of folks that have funded this research. The first three at the top here are all funding agencies themselves, and so they want guidance and input on how do they think about selecting between these products. When it comes to carbon conversion, one of the challenges is that there's such a plethora of different types of conversion processes and products that could be produced that they want help in thinking through how do we make decisions between these technologies and what are the trade-offs and what are the potential unintended consequences. X Prize, we've just finished up working with them to evaluate the technologies that they've had compete for their $25 million prize. And again, they were a broad range of technologies. We provided the LCA assessment of the carbon footprint of these technologies. And so this is a whole range of questions that we can ask with these types of tools. You know, first of all, should I even invest at all in these carbon conversion technologies? If so, which of them might be most promising given a set of future conditions? How can we improve? So how do you actually improve the technology development at that early stage to have the biggest impact? And then what are the business risks and market issues associated with that as well? And so we have a whole slate of things that we're planning to build. But just to give you a sense for some of our phase one work, we started out developing a generic template to actually evaluate these different technologies. So they're quite different. So we had to make a generic flow diagram where we start with capturing the CO2, any processing, and then we have a conversion step that sometimes leads to a secondary conversion step. And in some cases actually produces multiple products. And so we went through and actually collected this information, worked with technology developers to actually get the information we needed to represent this, and then tried to build a set of metrics to compare and evaluate these. And so in our first round, we actually assessed 97 different pathways. So it starts with different sources of CO2. Then moves to different categories of conversion. So you can actually reduce the CO2 using a variety of different materials. So hydrocarbons, hydrogen, other reagents, electricity, light. There's CO2 mineralization pathways that you can produce a cement substitute or those kinds of things. There's bioconversion. And then there's always new and interesting conversion steps that don't quite fit into this pathway. And then this is just an example of the types of products you could produce. They generally fall in the area of chemicals, fuels, and materials. And so these are the range that we looked at in our first phase. And then we also thought about 4 different metrics to evaluate these. And these are different ways to look at that same set of products and processes to give you a full perspective on the climate impacts associated with them. So the first one is, estimating the total amount of greenhouse gases that are emitted for every kilogram of CO2 that's converted into a value-added product. The second one is actually looking at it on a per product basis. So what are the greenhouse gas emissions that are going into the atmosphere for every kilogram or megajoule of product? So a kilogram of a certain chemical or a megajoule of diesel, for example. The third one is the avoided emissions. So if you compare on a per product basis, you might not actually be a net negative technology. You might not be ultimately removing CO2 from the atmosphere. But if your emissions from this carbon conversion process are better than the way we're currently producing that product, you're still delivering a mitigation opportunity. So you're still reducing emissions below how we would normally produce that product. And so that's still a valuable thing to be looking at and considering in this process. The third one then is the global emission reduction potential. So this is not just saying that, the difference between the emissions from a carbon conversion technology and the current method of producing that product are beneficial, but how large is the market by which you could actually deploy that? Because what we see is sometimes a product will be an order of magnitude lower in greenhouse gas emissions than the incumbent, but the market is very niche. And so the overall climate impact that you're going to have is relatively small compared to the opposite case where you have marginal reductions in your emissions, but because it's such a large market, you can have a pretty significant impact. And we see that with things like mineralization, where the cement industry is just so large, they're very greenhouse gas intensive. So any mitigation that you can do in that area can have very large global effects. So those are the 4 metrics we looked at. I'll just give you a couple examples because I do want to spend some time discussing this as well. This is using the first metric, so kilograms of CO2 equivalent that are emitted for every kilogram of CO2 that is converted. And I'll just note that we do have a beta tool available for this, and if using all 4 metrics of evaluation and some sample cases to look at on GitHub. So it's in beta form, but we do have a tool that you can actually, it's an Excel-based tool, so relatively straightforward, and you can look at different input energy sources and things like that if you're interested in this. And so this is what the results sort of look like as an example. And so these are greenhouse gas emissions, kilograms of CO2 emitted for every kilogram of CO2 that's converted. So the CO2 that's converted, we're giving all of them a -1 kilogram because we're assuming that that CO2 is actually being taken out of the atmosphere and converted into a product. And then the positive side of the emissions are different aspects. So you have the capture process itself and the energy that's required to actually capture the CO2. You have any hydrogen that needs to be produced to be consumed by your process, the CO2 conversion step itself, and then any end use. So if you're producing something like a synthetic diesel, when you combust that diesel in a vehicle, that's your end use emissions, like this orange bar here. And so this set of assumptions looks at low carbon sources of energy. So your electricity and your hydrogen come from low carbon sources. And you can see that we've got the net value here as the diamond. And so you're taking the emissions that go into the atmosphere on the positive side and subtracting that 1 kilogram. And you can see that some of the mineralization pathways actually do give you that negative value associated with that. So on net, they're reducing greenhouse gas emissions. But you can see that some of these pathways are still above 0, so that they're emitting more CO2 than they're actually converting. If we switch the assumptions to not from low carbon sources, but from, say, natural gas, you can see that many more of these pathways become net positive. And so that they're emitting more CO2 than they're actually converting, because the energy inputs that they're using have greenhouse gas emissions associated with them. So here is where you're actually supplying your hydrogen and your energy products using natural gas. You can see mineralization still tends to be quite competitive, that some of the bioconversion processes are competitive. Some of the electrochemical, you can see that they're very sensitive to the type of energy inputs that you're putting into the system. So lots of different pathways here, lots to discuss, but I did want to show this as sort of an example of the way in which you could make use of these systems tools to understand which of these technologies are most promising, as well as to understand if you're developing technologies in this space, if you have a solid oxide fuel cell that you're using to convert CO2 into products, where should you focus your effort in terms of reducing the impacts from your pathway? And so we work with fuel cell technology developers and give them that input input about the relative trade-offs. And so that first initial reduction of CO2 to carbon monoxide is actually not where the largest source of energy consumption and greenhouse gas emissions are. And so for that, we want to just reduce the costs and then focus on that secondary step of getting CO to a final product, where you have to oftentimes add a lot of hydrogen. So those are the types of insights that we can provide to the technology developers. The other metric I was going to show is just the kilograms of CO2 equivalent per kilogram of product. And so in this case, we're looking at synthetic diesel. And these are just a subset of the pathways. And I do apologize for all the acronyms. There's quite a bit in there. I can look through individual pathways with you, but just wanted to show that there's multiple routes by which you can actually create synthetic diesel. And then this last column here is the incumbent technology. So this is conventional production of diesel from an oil product. And so what we can do is actually look at each of these per kilogram of product and then compare it to the incumbent case. And so in this incumbent case, we have some of these processes that are actually, you're better off to do the CO2 conversion than you are to produce it using conventional means. Some of them are still above and need additional work on the technologies to become more competitive, as well as to shift the source of energy. So this is natural gas based, and energy and hydrogen come from natural gas. And in this case, we can see that they become more competitive if you switch to those low carbon sources. Right. So this allows us to understand, are we doing better than we're doing today, even if it's a net positive pathway? So our recommendations from phase 1 then are that carbon conversion technologies do hold promise to deliver meaningful greenhouse gas emissions mitigation. I actually came out of this project more optimistic about some of these pathways, but very much recognize that some are better than others, and the conditions really matter. So we do need to investigate these in a deeper way to understand which of them should we really be focusing on and incenting moving forward. The systems perspective is really important, and we need to look at that holistic picture of the source of the CO2, the activities that are occurring, and the products that are going to be most competitive. The metrics that we need to evaluate, obviously, we need to add the economics. We need to think about how do we actually think about these early stage technologies to scale them to what we envision the commercial performance to be in order to provide that valuable information. And so we are working as a consortium with industry, with academia, and with government to move that project forward. So just to wrap up, system tools, I would say, I'll leave you with this, that I do think that they are underutilized, and that we should be thinking about them right from the concept stage to help drive innovation. And all of these aspects that I talked about, I think could really help move the discussion further in terms of our energy transition, and help us make more efficient and effective technology development processes. So with that, I will thank you and be happy to take any questions that you have.
Thank you, Jewell. That was a really great seminar. A lot of topics. I was frantically writing down notes here to put some questions, but I want to ask the audience first. You can either unmute yourself or raise your hand, or type something to chat. Guess while people are thinking, I had a question about, it was slide 19 where you're talking about electric generation, and you had those Monte Carlo results, and you had coal, the next, that one right there. So I'm not familiar with what numbers are significant versus not. So one of the questions I had about this chart was your apparently best case is still some substantial net CO2 emissions. So are those good numbers? I mean, if the country has a net zero target, this reduces things, but does it get you where you need to be?
Right. Yeah. So I think that's a great point. I think that with most of these evaluations, what makes economic sense will not be to get each of these individual sectors down to zero. And I think that that's where the case for negative emission technologies comes in, is that getting that last bit. So if you were doing the coal with CCS today, or you had that breakthrough in your natural gas with the advanced carbon capture technology, you're getting pretty close to zero over that 50-year time horizon. And this is the cumulative emissions, right? So you know you're still going to have some emissions between now and when you hit carbon neutral. But even when you do that, you know, the breakthrough in the capture technology, you're not seeing that you're getting to 100% capture. And so there will still be some release of emissions associated with that. And either we need to push that technology to get to that 100% capture, but recognize we also still have to procure that natural gas, and that will have emissions associated with it. And most times there's going to be some fugitive emissions and things like that that we cannot eliminate completely. And therefore, there is always going to be a role for negative emission technologies. So I'd say that the scenario 3 and 4 definitely could get you where you need to be going in terms of carbon neutrality if you paired that with some negative emission technologies.
Okay, and I'm just realizing now, maybe another factor here is this is the 50-year cumulative. So a lot of your emissions could be front loaded because you're just implementing technology. And by the end of the 50 years, your per year emissions might be significantly lower. Is that also true?
That's right. Yeah. Yeah. So, and the trajectory of when you would do that, right? Scenario 4 assumes that we're going to do it. All of the capture would be put in place today. And the advanced technology means you switch over to natural gas and wait for the breakthrough in the carbon capture technology. And part of the breadth of that distribution for the black bar there is because we're not sure when that technology will come online. And so the trajectory of when those emission reductions will occur is uncertain associated with that pathway.
Okay, great. So Kishore has a question. I'll read it for him. You can unmute Kishore if you want to, but he says, how does CO2 to DME conversion fare? Does that make sense? It's in the chat.
Yes, sorry, I missed that. DME, yes. So we have in our base case pathways, we do have the DME there. Yes, we have it here. So again, it is on the higher side, even with the low carbon sources. So you can see when we switch to the natural gas based inputs, we can see it being on the positive side, but still has potential.
So you still need some hydrogen for the DME conversion from CO2. I guess that's what is penalizing it.
That, as well as the CO2 conversion process itself. And then if you're going to combust that as an end product, you would have the end use emissions as well. I can show you the low carbon sources.
So DME can be used in oil recovery. So if we use that for oil recovery and leave it in the ground, some of that yellow thing will go off. Right?
Yes, yeah. So this is where, you know, we've got a lot of pathways characterized here, but all permutations have not been, we haven't gone through all of them. So definitely you could put that in to produce oil, and then you would look at that oil pathway as well, right? But if you've made that oil pathway more efficient because of that, then you would get that credit against the incumbent technology.
Thank you.
Okay. See, do we have another question and get a graduate student to be brave enough to ask a question here? While they're thinking, I'll ask another question. So your colleague, Steve Bryant at Calgary, seems pretty hip on direct air capture. So, so these tools that you're talking about, so one of the questions there is the energy cost for direct air capture, and then also the, you know, just outright, you know, financial cost. Is this kind of analysis could capture that, I presume, so you could evaluate that?
Very much so. So we're looking here at this -1 value for the capture, But that depends on the sort of regulatory system and how you're viewing the system in terms of that credit, right? And taking CO2 out of the atmosphere versus taking it out of a surface processing facility that like an industrial source, where you've originally taken that carbon comes from the ground. You've introduced new carbon into the atmosphere in order to actually process it, and then you take that and put it back in the ground. That in different regulatory regimes could be treated differently than reducing the concentration of CO2 in the atmosphere. And that's sort of fundamentally the conceptual difference between direct air capture and an industrial source capture. And then, yes, definitely, we can substitute in different capture processes that will have different energy impacts. Right, so the direct air capture will have a much higher green bar because you're actually using a lot more energy to get that CO2 out of a dilute source like the atmosphere. In terms of the economics, we can also look at that. So we had a recent paper that was looking at direct air capture for synthetic fuels. And you can look at both the economics as well as the greenhouse gas footprint associated with those as well. So definitely it's well suited to look at that, but it does sort of confront this, that how you credit these things will be dependent on the regulatory regime in which you're actually looking at these systems.
Right. So some of the decisions might be skewed by the political environment you're in, I guess. If you think of that, the regulations follow the political environment.
Yeah, and I think that, with the direct air capture, you often get the reaction that why would you ever do it on such a dilute source? From a thermodynamic perspective, it makes sense to do every last stationary source that has a higher concentration before you would do the direct air capture. And there is some discussion that needs to happen there, because are you extending the life of the power plant that you're capturing from because you've put this capture system on, and therefore introducing more carbon into the atmosphere? All of those kind of issues come into play when it comes to these kinds of things.
I guess on the direct air capture side, one of the things, I don't know if this is Steve or it was Martin Blunt, I was talking to the two of them, they said that the nice thing about direct air capture is you can put the capture facility in a place that's good for storage. So the end use being storage as opposed to product, that might have an influence on your decision as well.
Yeah, and we see that with Oxy Petroleum investing in the direct air capture in the Permian, right? Is having it on site of the enhanced oil recovery rather than bringing in natural dome CO2, for example. Right, that's definitely
right.
A potential benefit, and might be a financial benefit in addition to allowing you to claim larger CO2 sequestration credits.
Okay, any other questions?
Yeah, can I ask a question, John?
Go ahead.
Ms. Carlos. Excellent talk. Thank you so much for taking the time to give us this beautiful lecture from the snowfields in Calgary. So appreciate that. I have, you mentioned Oxy, and my question is about this. Maybe I'm sure you know about what Oxy is doing and what they are marketing in terms of their carbon neutral work, their expectations for 2050 or maybe even 2030. And what's going on right now is that we have a moratorium on drilling in federal lands in the US. So based on everything that you know and you have studied, what would you say would be a good compromise between the policies of the new government in the US and achieving carbon mitigation the way Oxy is proposing to do it? I know this is a semi-political question, but I'm trying to get an answer from quantitative grounds, perhaps.
Yeah, so I think one of the innovative things that Oxy is talking about when it comes to enhanced oil recovery is the direct air capture, and that actually is removing CO2 rather than introducing new carbon into the atmosphere. And if you pair that with an enhanced oil recovery, particularly if that enhanced oil recovery is trying to co-optimize, so maximize oil production, but also maximize CO2 storage, you can definitely get pretty significant CO2 reductions. So that's not the way that we're doing it today. And I'm not saying that Oxy is necessarily going to change their operating practices, but there is potential to, right now the signal is to minimize the amount of CO2 that stays underground because it's a cost. And there's not enough benefit coming back in terms of the credit you get for storing that CO2. And if you could shift that component, then the direct air capture plus the storage that you get in that system actually could be very promising in terms of mitigating the CO2. Hopefully that is clear. I think that there is definitely a divergence of views in terms of whether the fossil systems even get to the table in terms of talking about mitigation. But of them, I would say that I would see that one, the direct air capture, enhanced oil recovery with maximizing the CO2 storage along the way. I would see that as one of the promising options to put on the table if I had the ability to do so.
Yeah. Of course, the Permian is an ideal place because we have so many wells and so many operations going on at the same time. But other times it's really hard to pipeline the CO2 elsewhere, right? But that's good for Permian Basin. Thank you.
Yeah.
So, thank you, Jewell. I think we'll end our formal question and answer right now. And if anybody wants to stick around for some informal questions, Jewell might hang out for a few minutes before she gets back to making snowmen or something. Actually, she said it was a very nice day. It's above freezing up there, 6 degrees C, right? You said?
Yeah.
So anyway, let me close with thanking you again. We really appreciate you taking the time to give us a presentation. So let me get my my Zoom hand clap here, but we really appreciate your time and work to put this together for us. So this is a very, very interesting topic.
Yeah, glad to be here. Thanks for the discussion.
So students or anybody else, if you want to hang out, that's fine. I'm going to actually ask a couple more questions about just the Canadian energy pictures, those early slides you put up, because I'm kind of interested in that. But
sure.
I don't want to dominate the conversation if somebody else wants to ask. I guess I'll just go ahead. So you mentioned the LNG idea for Canada, and I was just wondering, would that be direct competition with the U.S. for markets? Then I know that the U.S. is got a pretty stiff competition coming from the Middle East and Qatar. I don't know if in Canada would it be mostly West Coast export?
There has been some discussion about East Coast as well, just because Europe there's certain parts of Europe that are interested. And so I would say going both directions is on the table. There's been sort of fits and starts to the conversation, and companies have come in and paused and restarted projects and things like that. So it hasn't really gained enough momentum at this point, but I would say on both sides, we're seeing interest.
Okay. And I know that I was talking to one of our alumni talking about Gulf Coast and well, gas that comes from the Permian Basin going to an LNG port, and saying that France was basically saying they wouldn't take that product as LNG import because its carbon intensity was too high. And so I'm wondering if that would be a challenge in Canada as well, or at least if the gas is oil associated anyway.
Yeah, so I think there's differing views, and there is a moratorium on fracking in Quebec, and so there's quite a bit of divergence in that view. But there have been some discussions with European entities about non-fracked gas or low carbon intensity gas, and our Western Canadian assets have some of the lowest carbon footprint in the world. Really, we've been looking at that, and some of our tight oil, given the CO2 concentration in the gas, that reduces our footprint because we have low CO2 concentration, as well as a lot of our venting and flaring regulations. We actually do have some pretty impressive regulations in terms of the amount of venting, and working on the fugitive side as well, detecting and mitigating that. And so that does make the carbon intensity quite low in some of our Western Canadian assets. That message hasn't got out that much. I feel like when people think of Canada, they think of oil sands. But we do have, some competitive tight oil and gas in that space. But a lot of it comes down to the question of, is it fracking that you're opposed to, or is it the carbon intensity you want to look at, right? And so there's still that conversation ongoing.
Yeah, okay. Anybody else want to jump in with something? It's hard to see with the Zoom world here.
I do have a question, if you don't mind.
Yeah, go ahead, Carlo.
Yeah, my name is Carlos Torres Verding. Please say hi to Steve when you see him.
I will, yeah.
I don't know if he's enjoying the snow there. Tell him that we're very happy here in Austin.
He was out walking his dog earlier today, so
Okay.
he's getting used to it at least.
He always seems very happy when I see him, so I'm sure he's very happy there. So I enjoy very much your talk because you are doing a very good economic and also, I guess, efficiency, energy conservation, and all of those things that are very important for engineering. So that's grateful. What solutions would you propose that are out of the box in terms of much faster to mitigate CO2 much faster? For instance, we know that, I don't know if this is the same thing in Canada, but in the US, in the Permian Basin, there's a lot of flaring going on. And of course, this is methane. Some people don't like it. I don't like it myself because it's wasteful and bad for the environment. But are there any other solutions that, based on your analysis and experience, that could bring the CO2 mitigation much faster than proposed in the Paris Agreement or by Biden, say, in 2050?
So I think that there are no easy answers in this. I don't think there is one thing that we should be doing, in isolation. I think that, the way that I look at things is we need to be looking within our fossil-based system and our existing infrastructure for as many things we can be doing in that space to reduce the impacts as we look to integrate things like renewables. And I think, where I see the huge opportunity for students and for others is to look for those hybrid solutions where you can make use of the existing infrastructure, but integrate and your knowledge of those systems to integrate things like renewables in smart ways. And so one example is our hydrogen. We consume a lot of hydrogen in our upgrading and refining processes. And so we're the perfect place to be proving out the scalability of some of these hydrogen technologies, right? So leveraging the fact that we already consume it in a place at large scale, how do we then match the technologies and prove them out that way? So that's where I sort of feel like there's not enough dialogue going on. But I do think, within the fossil sector, we see that we will be using it for quite some time, and we're not spending as much time on those pathways to look for opportunities to reduce. So whether it's finding better uses for those gases that you're flaring and providing the infrastructure to make use of the gas rather than flaring it. There are some innovative flaring technologies that we're looking at within our department. But the methane side of it is important, but we also have the rest of the greenhouse gas footprint. And I think when it comes to fossil-based systems, we really need to think about that end use, which is, for the oil pathways, it's 60 to 80% of the emissions come from that side. And so while the oil sands companies are working very hard to reduce their portion of emissions, it is on the up to 40% of this life cycle. So if we don't deal with the 60%, we're still having a problem. And so I think that systems thinking of where do you get the biggest bang for your buck, and then how do we incorporate the emerging technologies and the renewable technologies within our existing system. To me, that seems like a place that we haven't spent enough time, and we should be spending time.
I totally agree with you, because right now there's confrontation between the environmentalists and the oil industry in the US and Biden. But, this confrontation could come to a peaceful agreement if we come somewhere in between. And that in between is the one that I'm very interested in finding, something that is socially, morally correct. And also it benefits the oil industry, and it benefits the current industry, and it propagates the transition of energy as well. So everybody will be in the same space of satisfaction, I guess. Yeah.
Yeah, I think that's a challenge. I think in Canada we see it as much as anywhere else in the world in terms of, colleagues of mine that work in the space of life cycle assessment and techno-economic analysis. Some of them feel that applying these tools to a fossil-based system is wrong to begin with, that we need to not look there and start just looking at the renewable space. And I think what I have tried to contribute are things like open source tools, so we can transparently see where do we get the biggest bang for our buck. And there is low-hanging fruit within the fossil-based sector that would make sense to do, while not saying that means that we're going to be using it longer than we would have.
No, that's actually true. Of course, being cynical and sarcastic, the other possibility is to do what GameStop did, right? On the, I don't know if you follow Wall Street, with all these things on Reddit.
It's hard to avoid that news.
Yeah, you don't have to follow Wall Street. It's on every headline.
But we can do renewables that way, right? To foster, I'm sure Mr. Musk is doing something like that, trying to foster renewables and by speculation. That's another element of the equation.
So I have one more quiz question for you here, Jewell. So I teach our freshman class where we talk about all the U.S. statistics for energy mix and also end use. And I don't know if I heard you right, but you were talking about 75% of some energy form going to industry. Were you talking about oil in Canada? That was back like your...
That was total energy.
Total energy.
Yeah, it's total energy in Alberta. Of all the demand, 75% goes to industry, which means that it includes our exports.
Okay. So you weren't talking about a particular primary fuel, you were talking about total energy.
Mm-hmm.
Okay. That still sounds a little bit high, but I guess it's part of it is that Canada's mostly an exporting nation.
That's right.
Smaller population compared to the US. So.
Yeah, and it's just Alberta, and that's where our challenge is, right? So our transportation, I had looked it up for Texas as well, and it looked like Texas was at 50% industry in terms of energy demand.
Okay.
And that's high for most jurisdictions if you looked at other states and other provinces. But our transportation is 11% of our total energy demand, and that is really out of line with most other jurisdictions. And so converting all of our vehicles into electric vehicles with a low carbon grid, that's not going to satisfy our climate demand in any way, shape, or form, right? It's really not the focus. Well, we should do that anyway, eventually. It's not, that's not where we have to target things. It's really the industrial side.
Yeah. Okay. Cool. Well, we should probably let you go on and enjoy the sunshine up there. It looks great. What Carlos is saying, I think it's like 60 Fahrenheit here or something like that right now in Austin. So
yeah, that also sounds nice though. I've never been to Austin. I would like to get there at some point.
Oh, yeah, that'd be great. Well, we're sorry we couldn't invite you in person for this event, but hopefully things will improve. That's the other thing. Not only do we need to figure out how to solve energy, but we need to worry about public health nowadays. So
yes, one challenge at a time, or maybe all of them at the same time. I'm not sure.
Well, thanks again so much, and we really appreciate it.
Yes, happy to be here. Yeah, nice to meet you. Take care.
Yeah, bye-bye.
Bye.